Hi, I'm Allen Mincer. I'm a professor in the Department of Physics at New York University, and today we're going to be looking at polarization. Light is an electromagnetic wave, so if that light is coming towards you, the electric field can be oscillating in this direction, or in that direction, or in any direction between those. There are materials that preferentially let light through when it's polarized in a particular direction. Let's assume we have light coming like that. And on top of this, we have a polarizing sheet. It's going through a polarizing sheet whose axis of polarization is at some angle phi with respect to the direction of the polarization of the light wave. The intensity of the outgoing light will be the intensity of the incoming light times the cosine squared of the angle phi between those two. If you have light that's not polarized, so in general light coming out from bulbs, from fluorescent lights is not polarized, it has random polarization, and that says the amount of each bit of light will vary according to what its cosine squared, what that angle is and the cosine of that angle. The average value of cosine squared of an angle over all possible angles is equal to a half. So an average for ambient light, the intensity of light coming through a polarizer will be about half the intensity of the light incident on it. So if you see me here and you see me here, I'm a little bit dimmer. It's hard for our eyes to see, but it's about half as bright as it was. Because the light incident on the polarizing sheet is at random polarizations, if I rotate this, then you shouldn't see much change in intensity. We're actually letting different light through when it's this way to when it's perpendicular. Right? And this way you allow light that's parallel to an axis in one direction. This way you're letting light through that's parallel to the axis in another direction. But on average that's the same amount, so you don't really see any change. Okay, you'll give me a 1, 2, 3 or something, or you're already rolling. Okay, now you tell me. Okay, so before we saw what happens when you have one polarizing sheet, now we have two. And the two are now set up so both of the polarizations are in the same direction, and it doesn't really make a difference if there's one or two. I don't know if you can see this. If I put my hand there, or if I put my hand there, you should see it by about the same amount. But if we start rotating the one that's closer to me, the polarization axes aren't aligned, and the intensity of light will fall as cosine squared of the angle between the two polarizations. So if I rotate this a little bit, it should seem a little bit dimmer and dimmer as I rotate. That's 45 degrees, so it should be about half the intensity. And if I keep going, then I should disappear completely. If I rotate it back, then I reappear. So now we've return these sheets so that they're polarized in the same direction. Hopefully you can see me. And we're going to add a third polarizer. And if I hold it in this direction, it's also roughly polarized in the same way. So if I put it over here, or put it over there, or put it over there, then you should see roughly the same intensity. If I rotate this, then at some point I'll be cutting out the light. And once again, whether I put it before the first polarizer, so that the light coming out of here is perpendicular to the axis of the first one, or I put it over here, so again it's perpendicular to the axis of the first one, or I put it here so it's perpendicular to the axis of the second one, then I've cut out all the light. Now what I'm going to do is rotate the one that's closest to me. So these two are now perpendicular, and you should see very little light. If all the polarizer did was remove light, then putting something in between the two shouldn't change anything. But the polarizer actually changes the axis of polarization of the light, which means that the light starts off polarized in some direction from the first polarizer, the one closer to me. It comes in perpendicular to the second one, and therefore no light comes out. But if I take this one and rotate it, compared to the polarization of the axes of the other, the light coming out of the first one will no longer be perpendicular to the second one. So when I do this, I've changed the polarization of the light, so some light does get through, and you can see it through the second one. So I have a little portable hole here. Again, if I rotate the axis, that will change, depending on how it is relative to the first one. But if I rotate it the right way, it's perpendicular to neither the first nor the second, and so it lets light through where it happens to be. The same thing is true for any size of polarizer, in particular if I use Polaroid sunglasses. So here I have glasses that are polarized, and they do exactly the same thing as these polarizing sheets do. They just cut out some of the polarized light. So if I start off with these two in the same direction, okay, then and if I put these glasses in between, then depending on what their axis is, right, whether I do it there or I do it there, depending on what the axis is, I can cut out more or less light. And similarly, if I rotate this sheet so that no light comes through, but I put the sunglasses in between the two, what it will do is change the polarization of the light coming through. So at some angles you won't be able to see anything, but depending on the angle I put it at, you should suddenly be able to see light just through the region where those glasses are. In this case, we're using the glasses to let more light through. Usually these glasses are used for the opposite reason. Light that's reflected is polarized, so you use polarizing glasses to eliminate light, and preferentially it eliminates the reflected light, which is already polarized, as opposed to the ambient light, which is various polarizations. So once again, I'm Allen Mincer at the Department of Physics at New York University, and today we've been talking about polarization.